Welcome. In this video, I intend to give a review and a summary of Chapter 7, which is related to energy and work. Well, remember we spoke about Newton's laws, and we said that according to Newton's laws, forces will cause acceleration. In other words, without forces acting on objects, we cannot change the state of motion of objects. And Newton told us that this is exactly how forces are related to acceleration. The larger the force, the larger the acceleration. If the force is small, then the acceleration will also be small. But then how exactly do forces cause acceleration? We define two important quantities. The first one is kinetic energy. And kinetic energy is given by half m, that's the mass, v squared, and v is the speed. That is the first quantity we define. And the second one is W, which is work done. Work done is given by the force times the displacement. So a force acts on an object and causes some kind of a displacement. Then the product of those two is the amount of work which that force has done. Now let's go on and consider, what is kinetic energy? Well, kinetic energy is the energy associated with motion. So whenever objects are in motion, we can associate energy with them, and that kind of energy is called kinetic. When an object is not moving, it has zero kinetic energy. We could actually test this out. Take this definition of kinetic energy and plug in the speed equal to 0. A stationary object will have zero kinetic energy, but a moving object will have a positive kinetic energy, which means the more the kinetic energy, the more motion, or the faster the motion. The faster the motion, the more kinetic energy an object has. Remember that the object will not change its state of motion unless a force acts on it. Using this idea of kinetic energy, we could begin to understand how forces cause acceleration. Well, the way forces cause acceleration is that when a force acts on an object, it will change its state of motion by either speeding it up, that is changing the speed, either speeding it up or slowing it down. And when you change the speed v, you will affect the kinetic energy. So now we could talk about acceleration from the perspective of kinetic energy. An object that is not changing its state of motion will have a constant kinetic energy, a fixed kinetic energy. But when you change its state of motion, what you will do is you will also change its kinetic energy. And of course, I should mention that kinetic energy is measured in joules, and the unit of joules is a compound unit defined by this, and also which is equivalent to Newton meter. That should be a 1 here. Should be 1 Newton meter. Now, what we have made a connection with is that a force implies a change in kinetic energy. And whenever we observe a change in kinetic energy, we know that it's got to be a force. A force is responsible for that. So this is a big important observation. That is, a force will cause a change in kinetic energy. And whenever we observe a change in kinetic energy, we know it is because a force is acting on that object. This kind of connection is qualitative. We would like to make a quantitative connection, like a numerical, in terms of quantities. Can we say something quantitatively about the force and the changing kinetic energy? Well, this is where work done comes in. Just to remind us, work done is equals to the dot product, or the product of the force with the displacement. The force that is acting on the object times the displacement that the object undergoes while it is under the influence of that force. On the top right here, I have an example where we have a box which is experiencing a net force acting on it. Before the force acts on it, the block was located at this position and it had a velocity or a speed of vi. When the force comes into the picture and pulls this object, the state of motion of the box changes. Hence, it accelerates. When it accelerates, its speed is going to change to a new value. That new value, while the force is acting, it acts so that the object moves from this position, from this first position, to this new position, and it undergoes a displacement of d, which I've signified with a red. When the object, the block, gets here, its speed has changed. It's no longer VI, but now it's VF. Because of the force acting over this distance, we observe a change in speed. The force has caused a change in speed, hence a change in kinetic energy. Well, we can actually capture this using the equations of motion. Look at what we learned from the equations of motion. One of the time-independent equations of motion is given by the final speed squared is equal to the initial speed squared plus 2 times the acceleration and the displacement over which the object is accelerating. Our case, we started off with VI here, and a force caused an acceleration A, acting on the block over a distance of D. If we make A the subject of this formula, we will come up with this. Acceleration from Newton. Things do not just accelerate unless a force motivates them, in particular a net force. So we could take this formula and plug it into Newton's second law, and what we come up with is something that looks like this. It looks a little messy, but actually it's very simple. This is just good old algebra. Now, in this equation here, if you were to multiply it by this value d, you could get rid of the fraction. What you're going to end up with is something that looks like this. We will be left with the force multiplied by the displacement equal to half mv final squared minus half mv initial squared. This is kinetic energy that corresponds to the final point, and this one is kinetic energy which corresponds to the initial point before the force began to act. Look at what we have now. This is a qualitative connection between the force and kinetic energy. It may well be the crown of the chapter. This box here is what we call the work kinetic energy theorem, because it quantitatively connects the work done by a force to the amount of change in potential energy. In other words, if we know how much work the force has done, we know how much the state of motion will be changed. This is essentially the crown of this chapter. Let's look at an example. Over here, I've chosen an example which demonstrates this idea of how to use this connection here, the work kinetic energy theorem. So we have a situation where they ask us how much work must be done to stop a 2-kilogram medicine ball, or you could just think of a ball, doesn't matter what kind it is. Its mass is 2 kilograms. Its speed initially is 7 meters per second. But what is our goal? Our goal is to stop. What does this mean? The initial state of motion is that the ball is moving at 7 meters per second. We are trying to change that state of motion so that its new state of motion is that it comes to a standstill. So what must we do? Well, remember the work kinetic energy theorem is that if you're going to change the state of motion, you have to do work. Okay, this is exactly what they're asking us. How much work must be done? Well, if we were to try to approach this problem head on, we will run into a couple of issues. For instance, by definition, work done is given by the force in question times the displacement. Well, in this particular problem, we don't have the force we need to apply, neither do we know the displacement over which we need to apply the force. So this direct approach is not fruitful. But what do we know from the work kinetic energy theorem is that whatever amount of work we need to do is going to be equal to the change in kinetic energy. Notice we have enough information to calculate the change in kinetic energy. If we could find the delta K, we know that delta K will be equal to the work done to cause that change in kinetic energy. So let's go ahead and calculate the change in kinetic energy. First, the initial kinetic energy is equal to half mvi squared. What was our initial state of motion, or what was the initial speed of the ball? Well, the initial speed was 7 meters per second. So we could calculate that. We're going to have a half. The mass of the ball is 2 kilograms, and the initial speed is 7 So what we have here is that this is going to be 49 joules. But remember, we want to bring the ball to a standstill. We want the ball to come to a stop. So we want our final speed to be 0. So this means our kinetic energy is going to be half mv final squared, which essentially will become 2 kilograms for the mass and 0 for the speed, which means our final kinetic energy should be 0. Therefore, let's calculate the delta K, which is the change in kinetic. Remember, change is always equal to final minus initial. So what is our final here? It's 0 joules minus, what is our initial? Our initial is 49. So we have 49 joules. Therefore, the change in kinetic energy is minus 49 joules. But they didn't ask us to find the kinetic energy. They asked us to find the work which must be done. But remember, the work done is related to change in kinetic energy by this crowning relation. So essentially, we could equate the two. This means we can say the work which must be done has to be equal to delta K, which is minus 49 joules. And notice the work done here is negative. What does this negative tell us? It's not telling us direction, because work done is not a vector, it's a scalar. But what this is telling us is the work which we are doing, or rather, the force which we are applying to do the work, is actually taking energy away from the medicine ball. Initially, the medicine ball had an energy of 49, but when the force was applied to it, it ended up with 0 joules. Therefore, the work which we did, it extracted energy from the medicine ball. And notice we were able to obtain this because of this important relation. I will stop this video here and I'll see you in the next one.